शेयर पे टाइम क्यों लगाता है तो इसको मैं डायरेक्टली कर लो तो
All right. Hello, everyone. This is Zafar Ali Khan. Sir Shahzada Bandashah is with
this
us.
is Bandashah-MYM.
Let us start. Today's lecture is about floating point representations. Few things that we should know before we go any further. To go about this lecture, it is necessary so few of the things what you should know already know prerequisites for floating point numbers study. First of all, you should know that what is denary to binary conversion. Obviously, you would have learned it in your O levels and AS level. Binary to denary conversion, already you would have learned it. 2's complement, maybe this year in A2s or maybe in AS, you would have learned it. Mainly we use this to put a sign on the number. Means if it is +3, we uh, use 2's complement to find out what is -3 in binary form and vice versa. There is a misconception that 2's complement is always used for just the positive to negative conversion. That's not true. From negative to positive conversion in binary form also uses 2's complement. So then in binary additions, you should have an idea of carry and borrow. Binary additions are mostly for either a nibble, 4 bits, or 8 bits. We don't have more than these bits for binary additions. You should have an idea that computers microprocessor cannot do anything other than addition. So in order to subtract a number, what we do that we find the 2's complement of the number that needs to be subtracted and we add it. And then with this uh, addition and subtraction, we further go about multiplications and divisions. So the CPU can only do additions. That is why we call it binary additions, not binary subtractions, not binary multiplications. The name of the topic is always binary additions. Then we should know what is the standard form. The standard form as in 23 into 10 to power 3, where 23 is a significant, and technically we call it mantissa, and uh, power 3 is the exponent. We should know about that form. Now, key terms. Key terms that we have today are binary floating point numbers. Binary floating point numbers are, as we know that these are the numbers that we use to represent real numbers. So a binary number written in the form mantissa into 2 to power exponent, and that number is actually the real number data type. Then we have mantissa. Mantissa is the fractional part of the floating point number. We will discuss about it, and it is actually with the point, a fixed point between first two bits. Then we have got exponent as in the standard form. It is in our number system, it is with the base 10, but in binary it is the power of 2, that the mantissa part, uh, the power of 2 that the mantissa is raised to in the floating point number. Then we have got normalization. This is normalization. This should not get confused with the normalization in databases. This is the normalization in floating point. In floating point, we have a method. Normalization is a method to improve the precision of binary floating point numbers. Positive numbers should be in format 0.1 and negative numbers should be in 0.1 should be in the form 1.0. Then we have got overflow. Overflow is actually the result of carrying out calculation which produces a value too large for the computer's allocated word size. Word size is the amount of bits that are given to us for holding up these floating point numbers. And then similarly, underflow. Underflow is the result of carrying out calculations allocated calculations which uh, produces a value too small for the computer's allocated word size. Now, these were the key terms: binary floating point numbers, mantissa, exponent, normalization, underflow, overflow. And then what we should know is, hold on, let me share this.
सर आपकी आवाज थोड़ी कम आ रही है.
Now, up say. So what you should already know: binary to binary conversion, binary to denary
Yeah.
conversion, two's complements, binary additions, standard form, representation, significant, and exponent. Now it is okay, Sir Shehzada? Voice is okay?
Yes, it's better now. It's better. It's better.
This is better. And then we have key terms: binary floating point numbers, mantissa, exponent, normalization, overflow, and underflow. Key terms we will go about now, but these should be known beforehand. Now, let us start. First thing that we should know that real numbers are not reliable, in a sense that if we are actually using any monetary values to be stored, it is not reliable. For that, we use fixed point numbers. So now, as you will learn in lecture today, it is nearly impossible to represent decimal values exactly in computer memories which use the binary number system. We will discuss how normally this doesn't cause a major issue, since the difference can be dealt with. As with the calculations in physics and maths, we used to round off numbers. What happens then representing monetary values in computers? Exact value needs to be stored to prevent significant errors from accumulating. So let's say if there is a bank and it is leaving 0.0001 cent per account per day, and there are millions of transactions every day, that 0.0001 will accumulate and will become a significant figure over days, years, sorry, months, weeks, years, and that would cause a significant damage. So monetary values use fixed point numbers. For example, we will discuss about it towards the end when we discuss that what are the errors that we face when we deal with floating point numbers. So before we go any further, let us discuss fixed point and floating point. Fixed point is actually when we like to save a number, which is, hold on. Actually, let us first discuss fixed point. Shahzada, this screen is appearing?
Yes, sir, it's there.
Actually, a fixed point is the representation of binary coded decimals. binary coded decimals, but we are not going to discuss that binary coded decimal. We are going to discuss this in just general terms, only general terms. In another lecture someday we will discuss binary coded decimal BCD, then we will discuss it in details. But the solid idea is that for every single digit in a real number, a decimal number, we use 4 digits to represent in fixed point. So let's say if I have got 10.3, if I have got 256.25, if I have got 1025.369, if I have got 50,246.2569. What you need to understand is the point is fixed at its place, and hold on. So that is okay. So point is fixed at its place, decimal is going towards the right, and the whole number is going towards the left. Now what is happening, that if we take a single number at a time, let's say 50,246 is being, and we have no idea that where the point would be. All right, so we cannot predict the decimal place in a number. So this is a fixed point number. In floating point, what happens that we actually move the point towards a fixed position so that we have an idea that where the point lies. So whatever the number that is given to us, we should find the fixed point notation of it in lane terms, not in BCD terms, and then we go further and convert it to the floating point. What does that mean? First thing that you need to understand that things like 3 uh, and this 6, 9 and anything which is being represented by binary should be the perfect factor of 2's power. Otherwise, we cannot represent it in binary form. So in floating point. All right. So what you need to know is first this. In the binary form, in the binary form, we use the base 2, whereas in our denary form, we use base 10. So what basically happens that this point lies in the middle, and then we have 10 to power 0, 10 to power 1, 10 to power 2, and we go further towards this side. Over here, it is 1 over 10 to power 1, 1 over 10 to power 2, 1 over 10 to power 3, and this goes further on this side. So when we move towards the left, we are increasing the digits worth by the factor of 10, means 1, then 10, then sorry, unit 10, 100,000, and 10,000. And if we move towards the right side, we decrease the value, the worth of the digit by 10. So this is point 0.1, point 0.2, point 0.3, and so on and so forth. Now, if we take it with respect to base 2, point is there. So this is 2 to power 0, 2 to power 1, 2 to power 2, 2 to power 3, and this goes on towards the left side. And if it is on the right side, then this is 2 to power 1 over 2 to power, sorry, 1 over 2 to power 1, 1 over 2 to power uh, 2, 1 over 2 to power 3, 1 over 2 to power 4, and this goes further. So if we solve it, this would become 1, 2, 4, 8, which goes further, and this would become 0 0.5, 0 0.25, 0 0.125, 0 0.0625, and this goes further. So if I like to make a number denary 10.25, I would actually be achieving it in fixed form as 8 plus 2, 10.01. So this 1 is being multiplied with 0.25. So this represents 0.25, whereas for the 10, as usual in denary to binary conversion, the 0 multiplies 1, the 0 multiplies 4, 1 multiplies 2, and 8 multiplies 1, and 8 plus 2 becomes 10. So if it is in the denary form, in binary form, this would be equivalent to 1010.01. So this is fixed point representation. This is a lousy form of fixed point representation. Actually, fixed point we are just using it as a reference over here so that we could continue with our uh, topic further. So whenever you are given a denary decimal number that we need to convert to its equivalent binary floating point number in decimal form or real number, we first convert that number to its fixed point representation, and then we convert it from fixed point to the floating point representation. Remember one thing, that floating point numbers are actually the real numbers. Different languages have different data types for these floating point numbers. In Visual Basic, it is single, which allocates 4 bytes for representation, where 3 bytes are in mantissa and 1 byte in exponent. Why 3 bytes in mantissa and why 1 byte in exponent, we will discuss further. And then there is another data type, double, and that double has got 8 bytes, where first 7 bytes are for mantissa and 1 byte for exponent. Similarly, in Python, there is a type float. Every language has got size limits, so they give us chance to opt out of different floating point representations. Like in VB, it is single and double, and sometimes it is quadruple. So as per the need, how large mantissa do you expect in your calculations, how large exponent do you expect in your calculation, that is all need to be considered. So one point that we have established over here is that we need to find the fixed point to find the binary representation of it in floating point. hold on.
सर जो डेसिमल पॉइंट्स हैं वो अकॉर्डिंग टू आवर सिलेबस अप टू 5 पॉइंट्स तक है ना, 0.312 उससे ज़्यादा नीचे तो नहीं जाते हैं
सिलेबस में?
हाँ, अकॉर्डिंग टू द सिलेबस अगर हम बात करें तो
हाँ,
डेसिमल पॉइंट
पॉइंट के बाद आफ्टर द डेसिमल पॉइंट 5 फ्रैक्शंस वी नीड टू
5 फ्रैक्शन
remember. Yes, 5 fractions. Hold on.
Sir, your voice is closed, Sir Zafar. Okay.
All right. Let's cut the clutter first and then start studying this. So as we know that we need to convert from fixed point to floating point. Let's say we are given with this number 19.187 and 5. So what's actually happening over here is we know about this. I just described it that when we go from, if it is the point, when we go towards the left, it is usual binary conversion. And if we go towards the right, it is actually reducing the number by half. So this is 1, 2, 4, 8, 16. This is 0 0.5, 0 0.25, 0.125, 0.0625. It goes as much as you want it to be. So 19 has to be 16 plus 2, 18 plus 1, 19, and 1875 you will achieve by having this fraction 0.125 and 0.0625 added. So now before we go any further, we now know that we have to find the fixed points to floating point conversion. So whatever the number that is given to us needs to be first converted to the fixed point. So this is the fixed point formation. So this will help us to find the fixed point of floating point number here. Now this fixed point is not in term of BCD. This is just a fixed point in a lousy lame term, which is actually used as ad hoc term over here to represent literal conversion from a number which is real in denary form to its binary form, to see it in its binary form. Now, before we go any further, we need to understand that floating point numbers are having this form. All right, so we have got uh, a number of bits allocated for floating point representation, and the whole collection is called word size. So the word size for this floating point number is, let's say, 16. Now what is happening out of these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this is the word size. So out of this word size, few bits are allocated for exponent, as in the standard form, and few bits are allocated for mantissa. So what is the purpose of it? Let's see. Mantissa requires you to have the part of the significant in it, and exponent requires you to have a part of exponent as in standard form with it. Okay. Now, let's say, what does it mean? Let's say in denary we have got this number 2000. This is standard integer form. If I write in standard form, this would become 2 in 2 into 10's power 3, where this 3 is supposed to be what? The exponent. Shahzada, is it clear now?
Yes, sir.
This 2,
Yes, sir.
this 2 is it clear? You can listen and you can see it.
Hello.
Is it clear? You can see and listen to it.
Sir, I can see the screen, but what I'm feeling little bit कि जो आपकी आवाज़ है वो थोड़ा सा flicker कर रही है. Maybe it's because of at my end. Live stream में सही जा रही हो. Hopefully.
Yeah, on my side it is okay. On my side it is okay. So now जरा comments देखते रहिएगा please. This is called significant but in our syllabus this is not significant, it is rather, this is base. Since this number is in denary form, this is base 10 number. So we use this one, and this multiply implies that these are to be being multiplied together. Now, if we go with a form which is in binary, let's say we have got 10.5. So first we need to have a binary of it 1, 1, 2, 4, 8. This is 10 and this is 0.1. This is now 1010.1. This is the standard fixed point binary representation. Now, what actually happens, what is required, that we should move this point all the way towards left without thinking of anything. All the way towards left without thinking of anything. All the way towards left. Why all the way towards left? We will discuss shortly. So this would become 0.10101. And the point has traveled 1, 2, 3, 4 positions. So this would become into 2 to power 4. What is actually happening in this form? This is actually in the binary, let's call it binary standard form. Now what is happening, that this exponent tells that how many times you have to move the point. If the exponent is positive, then towards right, and if the exponent is negative, towards left to get the actual number back. As in this representation, we understand that 2 is having a point towards its right. So this is actually 2.0. And exponent is positive 3. So it means that when the point from this 2's right side will move further 3 points, we will add 3 zeros to get this 2000 back. Similarly, over here in this binary standard form representation, the point and the exponent is positive 4. So we will move this point 4 points towards the right, 1010.1, and we will remove this exponent part. That will give us back this number, and from this number we can simply calculate what was the exact number in denary form. So this exponent implies that how many times this point has to move towards right or towards left as per the charge of this. So if it is positive, then we will move the point towards the right to get the number back. And if it is negative, we will move the point towards the left to get the number back. Now, so as we now know that this part is mantissa. Mantissa means the part which is showing um, uh, the part other than the exponent part. So this is mantissa. This is mantissa over here as well. And this one is exponent. All right. So whenever in binary we say floating point has got two parts in the word. Word is the total allotment of bits to one single floating point number. As I said that if we take single in Visual Basic, that would be mantissa and one in exponent. So now let's talk about it. If I go with this 1, 2, 4, 8, 16 towards the left, and 0 0.5, 0 0.25, 0 0.125, 0 0.0625, and 0 0.03125. As we know, as you would have already seen, that the point is fixed between first two bits of the mantissa. We also call it radix. So radix lies between first two bits. It is fixed between first two bits. Why? We will discuss about it shortly. So a mantissa, when it is representing number, it is actually representing numbers by having all the fraction after the first bit, and it is moving towards the right. So that means that in mantissa, you are actually representing this. Your number is actually representing this part. In this deal, this part is being represented using mantissa. So this is your mantissa, where the point lies between first two bits. Afterwards, this part over here from 1 towards the left, 1 towards the left, 1, 2, 4, 8, 6 is representing the exponent. So this is your exponent. And as we know that these numbers are actually in 2's complement form. So if it is mantissa, then this one will be negative. As we know that in uh, 2's complement form, the leftmost or the most significant bit is always having a negative charge on it. And similarly in exponents, and it is integer 1, 2, 4, 8, 16. So this 16 will be negative. So over here, all the values are in fraction, but they are on the right side. So leftmost bit is in mantissa is 1. So this 1 will be negative. Now, as you can see over here, now the question raises that how many bits are allocated for exponent and how many bits are mantissa, how we will define it or we will assume it. No, we won't be assuming anything. It will be given in the question that how many bits are allocated for mantissa and how many bits are allocated for the exponent. All right, so we don't have to worry, but this is one sure thing that the point lies between first 2 bits of the mantissa, and that is why in fixed form we move the point all the way towards the left to have it in between first 2 bits. Why, we will discuss shortly. Now, as I described in this figure, uh, the previous figure, that this is always -1 and this would be 0.5, 0.25, 0.125, 0.0625, 0.03125, and this would go towards the right side. Whereas this exponent will be 1, 2, 4, 8, 16, and this would be always going towards the left side. And in both of the cases, the numbers, the powers, the values which are given are actually in 2's complement form. So mantissa, because of this point in it, it is in fractions form, and exponent because it is just noting the number of times the point has moved or will have to move. It is just an integer. So mantissa has got point in it, it is fraction, and exponent is an integer or whole number as a whole. Now, uh, they both are in 2's complement form. Whenever we fill mantissa, we fill it from left to right. And whenever we fill exponent, we fill it from right to left. So we fill it from right to left, and mantissa, when we fill it from left to right. This needs to be remembered. All right, I call it floating point chemistry, and this needs to be in the mind all the way towards the end of this lecture and topic. So we fill mantissa from left to right and exponent from right to left. And let's say sometimes we have got situation that the number of bits that we need to fill in are more than the allocated space in the mantissa. In that case, we start filling from left to right and to the last bit available to the mantissa. And if we have got more bits to be filled, they will get dropped from the right. It doesn't happen then those bits enter the exponent part. No, exponent and mantissa are two different numbers, and they are then their places and spaces are being well guarded. So mantissa, that situation when we have got more to fill and less space that we have in the word, we call it overflow. And sometimes we have got the mantissa which does not fill the whole space. So in that case, whatever the number of bits left, we fill them with zeros. That is called underflow, when we have got less to fill and more space to accommodate it. All right. So now let's start solving this question. So we have 19.1817, 1875. So 16 plus 2, 18 plus 1, 19. And then we have got 1875 that we can achieve easily by having 0.125 and 0.0625 added. All right, so now this is the fixed point. Now we have to convert it to the floating point. In order to convert it to the floating point so that we could have this point fixed between first two bits, we will move it all the way towards the left. This will make it 0 point. Remember to put 0 there because this 0 is actually the sign bit. If it is 0 here, it means that it is a positive number. If it is 1 here, it means it is a negative number. So whatever, you have to move it all the way towards the left. And we know that when we move all the way towards the left, point will be here. So we have to put a 0 there. So this would become this. Since the point has moved all the way towards the left, this has now become 0.100111111. Now, how many times the point has moved? 1, 2, 3, 4, 5. So in order to get this original number back, we have to move the point 1, 2, 3, 4, 5 times towards the right. So we have to have a, an exponent which is positive 5. All right, so this is our exponent. So this is our standard form, but this standard form is having a point and multiplication and this 2 base and this 5 in the denary form, which is not the perfect representation of the floating point in this case. So what basically happens that this point, this multiply and this base 2, these will be removed and rest will be saved in binary form. Why they are removed? Because it is understood that this point is between first two bits. That is why we moved it. So we don't have to, there is no such representation in this word for floating point or in this allocated space of floating point which could show point. So we fixed it. We fixed it in between first two bits. So if it is written 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, it means that the point lies between first two bits. This multiplication is in standard form, it is a must, so we don't need it, we know it. And the base is 2 because we are dealing with binary number, the base is 2. So what we do, we just put it this way. We just put it this way. We remove this point, this multiply and this 2, and we convert this 5 to its binary form. And we use this space to signify that this is mantissa part and this is exponent part. So now one thing that is actually very important, the actual conversion of 5 is 1 to 4, but we have to put this 0 here. If you won't put 0 here, because this number is in 2's complement, that would become 1 to minus 4. So every positive number which is in binary form has to have this leftmost bit 0 added to it, so signify that it is a positive 2's complement form. If it is not, then it means that it will become a wrong number to be shown in 2's complement form. So this is actually very, very, very necessary to put a 0 there. So now this is floating point number, which is representing 19.1875. Now we have to put this number in the allocated word or the space which is given. So how do we put it? I told you that the numbers are already in 2's complement form. So we have to first find that how many bits are available for mantissa and how many bits are available for exponent. Now we will start filling it from left to right, the mantissa and exponent from right to left. So let's see how many bits are allocated. So the word size is 16 bits, out of which 10 bits are available for mantissa and 6 bits are available for exponent. So we will start filling it from left to right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, fortunately, we have got as many bits in mantissa as the allocated space. So we will fill it from left to right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is filled. Now we will start filling exponent. In exponent, we would have underflow because we have got 4 bits to fill and 6 bits to 6-bit space. So, but we will start from right to left. Remember this law that when we fill Mantissa, we fill it from left to right because numbers are increasing on the right side and actually decreasing in Mantissa. And in exponent, numbers are increasing on the left side. So we will fill it from right to left. So this time we will fill it 1, 2, 3, 4. Now this is the actual number that we wanted to fill. And this is 1, 5, and 2, 6. So we filled it from right to left. These 2 bits were filled because we had an underflow, because we had less to fill and more space that we had. Now this is a perfect representation of what 19.1875 in floating point. Before we go any further, you need to understand that the usual microprocessor has got an ALU, arithmetic and logic unit. Arithmetic and logic unit is supposed to handle all the mathematical tasks. It is said to be the hands of microprocessor. So it does everything, all of the arithmetic, all of the mathematics that the processor needs to do. And as we know in modern computing, it is all about the calculations that are being carried out by the computer. But the thing is that ALU, its arithmetic unit is only able to deal with integers. It does not deal with fractions or the numbers with point in it or decimal numbers. So for that, there is a device called floating point unit, FPU is used. And before that, before Pentium's invention, Intel Pentium processors, there used to be a chip called Math coprocessor in 286, 386, 486, 386DX. These Math coprocessor used to do this job. So whenever the processor has got a real number, a decimal number, a fraction number, it sends it out to, it used to send it out to the Math coprocessor earlier, and nowadays it is being sent to FPU, floating point unit. Remember, the speed of supercomputers is being measured in floating point operations per second rather than mega or gigahertz. All right. So ultimately, when it comes to complex computing, it is not about the speed, it is about the ability of the computer to resolve complex expression in less time. So anyways, let's get back to it. Every processor has got FPU in it inside the same jacket as per its cores. But it is not the part of the processor, it is outside the processor. It is inside the jacket, but outside the core. So this is the representation. Now, I told you that this leftmost bit in Mantissa over here, it is actually the sign bit. If it is 0, it means that the whole number is positive, and if it is 1, then it is negative. Now let's take 3 minutes and solve this. 36 plus 36.5625, and obviously this 19 was also a positive number, 19.1875. This will be saved same way, this will be developed same way. Please take your time. I am going to give you 3 minutes for it. Plus 36.5625. So Sajada, I believe we need more episodes for this floating point to recover.
हाँ सर, इसको आज अगर हो सकता है तो थोड़ा सा कट शॉर्ट कर लेते हैं, क्योंकि इसके बाद हमें नॉर्मलाइजेशन आई गेस अभी स्टार्ट करनी है, उसको प्रॉपर्ली लेकर चलना है.
हाँ, we actually let's go for about 15 minutes more minutes with the lecture, and then we will take questions for another 15 minutes.
ठीक है,
Then we will
ठीक है.
continue in next episode on Tuesday. All right, 3 minutes are over. So let us start further. So let's take the same number 0100111111 000101 and go further and go backwards. Now we will go from floating point binary representation to its denary representations. Now, zero one double zero double zero double one double zero. Now, if we go backwards, first we need to put point over here, and then it will become 2 to power 6. It's a different number, sorry. So 0 0.1, 1001001. We don't need these two zeros over here, as they will be just redundant, as they were used to fill the space that we had. All right. So we don't need them, as we know that Mantissa is filled from left to right. So these two has no significance as outside this word of floating point. Similarly, all these zeros towards the left in exponent have no significance. So this would become 2 to power 6. So 1, 2, 4. 2 plus 4 is 6. So this is the backward point. Now, in order to resolve this standard form, we will move this point 6 places towards the right. 1, 2, 3, 4, 5, 6 over here. 1, 2, 3, 4, 5, 6. As I said that if the exponent is positive, it means that point will go from left to right. 1, 2, 3, 4, 5, 6. So this will become 1001001.1, and this part of exponent is now resolved. Now this is let's say fixed point in binary form. All right, so this is 1, 2, 4, 8, 16, 32. So this is 1, 2, 4, 32 plus 4, this is 36, and this is point over here, so this is 0.5. So this has become 36.5 positive. Why positive? Because the original number had a 0 uh, at the start. All right. So now a bit of theory with it. These floating point numbers are non-reliable, as I discussed earlier. If used for financial data storage or monetary data storage in accounts or other things, as larger fractions tend to lose accuracy. Floating point mostly are used in stats, graphics, real data types, and gaming engines and etc., where exactly the perfection in fractional numbers is not required, and we have liberty to round off numbers. If we don't have liberty to round off numbers, then we uh, can use floating point. Otherwise, we have to use a fixed point in BCD form. Now, so this was from binary floating point number to denary real number. Now, negative floating point. Negative floating point is actually having a sign to signify that this is a negative number. Now, this is negative denary real number. So the rule says that ignore the sign and solve it like a positive number, and afterwards, once you find the answer, we will do something with it. If you do remember from 2's complement, the flipping rule, go from the right side to the all the way to the first one and keep from right side bit to the first one same and toggle the rest towards the left. That we will use in Mantissa to convert this number back to this negative form. Now, 8 bits mantissa and 4 bits exponent. Now, let's just ignore the negative sign and solve like a positive number. So let's take just 20.75. So 20, 16, and 4. 1, 2, 4, 8, 16. So this is 20. 16 plus 4, it is 20. 0.75. That means that 0.5 and 0.25. So 16 and 4, 20 and 0.75. 0.5 plus 0.25. This is 75. Then we have to move the point all the way towards the left, as we know that we have to move it to the position where it could be found between first two bits. It is sort of something fixed in Mantissa if we are converting it to floating point notation. Now, this would become 0.10100 point 0.1010101011 into 2 to power 5. Exponent is 5. Why? Because 1, 2, 3, 4, 5 times we move the point towards the left, and in order to get back the figure, we have to move it back 5 times. Now, this is the form. Let's convert it to its binary equivalent. Now this is, as we know, that point is fixed between first two bits, so this will now not be shown. Similarly, multiply and 2 are gone, and 5 is converted to its binary form. But remember with the 0 on the left, so that it is positive 5. Now, how many? We have got 8 bits. So we will start fitting it in 8 bits. All right, let's first convert it and then we will fit it. So now, as the original number was negative, this is positive numbers representation. So we will keep the exponents same, and in the Mantissa, from the right side to the first one, we will keep it same and toggle the rest. So we kept the exponent same and from the right side to the first one, we will keep it same in mantissa and toggle the rest. So first one will be, coincidentally, the first bit is 1. So it will be kept this way, and then rest of the bits will be converted. So 1 becomes 0, 0 become 1, 0 become 1, 1 becomes 0, 0 become 1, 1 become 0, and 0 become 1. So this is negative 20.75. Remember, if we are given a number that is negative, we solve it like a positive number. Once we reach to the floating point representation of it, we keep the exponent same, and the mantissa, we do some two's complement stuff, that is to convert it to the negative form. In the mantissa, from the right side to the first one, we keep it same and toggle the rest. So this one will remain same. This one is there at the first position. So one is there and rest will be toggled. So this is your answer. All right, so 1, 2, 3, 4, 5, 6, 7, 8. This is already filled, and we had 4 bits here. This is your answer. Now, negative floating point number, and we have to convert it back to the form which is understood in denary. Again, this is in this form where the first bit is 1. This first bit 1 tells us that this number is actually negative. So if you see a number that is negative in floating point, let's first convert it back to the positive form so that we could solve it this way. So we will, as the rule says, for the 2's complement conversion from negative to positive and positive to negative in floating point, to keep the exponent same, and toggle to the first one, sorry, in the mantissa to the first one, keep it same and toggle the rest. So we do the same. We kept the exponent same, and to the first one, we will be keeping it same in mantissa and toggle the rest. So this is the positive form of this negative floating point number. Now let's solve it this way. All right, now 0.10101, we will ignore these zeros. 0.1001 into 2 to power 4, 124. And then in order to dissolve this standard form, we will bring this point all the way towards the right. Sorry, or not all the way, but to the 4 bits, 1, 2, 3, 4. So this would become 10101. 1010.1. So this is your number in fixed form. Now convert it to the denary form, 1, 2, 4, 8. So this is 8 plus 2, 10, and this is 0.5. But we will be going to put a sign, negative sign there, so that this becomes the exact conversion of this negative floating point number to negative real number in D. Now you may go ahead and solve these questions. There are 1, 2, 3, 4, 5 questions from denary to binary, positive denary to binary, negative denary to binary, negative binary floating point to denary, and positive floating point binary to denary, and negative floating point binary to denary form. So let's call this lecture off for for today, and we will continue in next episode for the same lecture from this point onwards with a little revision of the previous lecture. Let's see, Shehzade, if there is or there are any comments or questions. Do you see any?
So just give me a second. No, sir, there are no
All right,
questions.
people can ask these questions later through their WhatsApp groups, or this chat will always be there. So if people like to ask questions, maybe after resolve these questions, they might have a few queries. Okay. So there is a question by Omar Farooq. Exponent in positive and negative difference. Yes, we will discuss it later, Umar. Uh, all the variants, what if a positive mantissa and negative exponent, what if a positive mantissa and positive exponent, what if a negative mantissa and positive exponent, and what if the negative mantissa and negative exponent. All those variations we will cover later when we will be discussing ranges. All right, so if, or maybe if I have gotten it wrong, you might be asking that what happens if the exponent is positive, we move the point towards the right side, and if the exponent is negative, we move the point towards the left side. Until now, we have just discussed all the questions with positive exponents. So we will discuss questions with negative exponents later. Any other question? So let me stop sharing my screen. I hope that, okay, sir, I will tune in next class. Okay, good. So let's call this episode off. We will continue on Monday with the next episode and to cover this topic, hopefully. All right. Thank you very much, everyone. Take care.